Start, everyone. Thank you, everyone, for joining us for February's DataWorks Maryland meetup. Really honored to have Lack from Google here discussing machine learning design patterns and designing machine learning infrastructure. Lack is definitely an expert. If you Google him, you will definitely find a number of interesting talks and articles and books, Medium posts. Very, very proficient author. Definitely an expert in the field. I think as recently as a couple of days ago, there's some recent interviews. So if you want to learn more, there's definitely a lot of resources available. To get started, I usually just like to introduce the sponsors for the group and just do some quick overviews. So we're definitely a sponsored meetup. We got a couple groups that are companies that work with us. Variant Technologies, they're a defense contracting company out of Maryland that do a lot of software engineering, data science, working with different agencies and customers. So if you're interested, please reach out to myself or email the info email address on the screen. ClearEdge is another one. They actually were one of the speakers last month when they were discussing some of the work they were doing with malware and data science, which was really interesting and available to view if you guys are, if anyone's wants to watch it. They also do some government contracting, some different work with data science, big data. They're kind of known in our area for that. So if you're interested in learning more about what they're doing, you can reach out. They do some interesting IRAD also that folks might be interested in learning more about. And then I usually just put my company up. We're a smaller company, but anyone that's interested in learning more about what we're doing, or myself, or what our industry is, I'm always willing to reach out and talk to some folks. I love sharing and love meeting people, so never hesitate to reach out. Rolling right along, so we got a couple other meetups scheduled. Next month is going to be data science product management, so a little different spin than what we kind of do. Another interesting O'Reilly author. And then in April, we're trying to do a pitch meetup, which hasn't gotten a lot of signups yet, but I'm really hoping folks kind of get interested, where basically if you have a product or a project or a company or yourself, really, you just can get on and you can pitch. We'll give each person a couple of minutes and then we'll take some questions. And the whole goal is to let the community meet each other. So I'm kind of excited about that. If you're interested in helping at all, just send an email to the info@dataworksmd.org. We're trying to do things with conferences and newsletters. I can always look for help. And if you're just interested in learning more about what's available, just reach out. So pretty quick. So with that, Lack is the director for data analytics and AI solutions on Google Cloud. His team builds software solutions and for business problems using Google's cloud data analytics and machine learning products. And he founded the Google's Advanced Solutions Lab ML Immersion program. Like I mentioned, a lot of resources out there for him. I'll try to share that as I capture, but definitely some awesome talks out there. If you look at his book, there's some really interesting design patterns. So the way that we're going to do it, just quick logistics. I am monitoring the chat on Zoom and also on YouTube. So if you have any questions, just type that to me either publicly or privately. I'll capture them all. And at the end, we'll ask Lack all the questions. So with that, I'm going to hand back screen sharing to you, Lack, mute myself, and you can take it.
All right. Thank you, Jason. It was great, and I love the amount of activities that you have planned. Like the pitch is a great idea to basically meet folks in the community and also know who else is working on similar problems. It's for everything that we talk about being remote and working remotely and all that, there's something about a sense of place, and being able to meet somebody over for coffee and talk to them is incredible in terms of the bandwidth and amount of information that you can impart. So that's great. Today I'm going to be talking about machine learning design patterns, and basically from the perspective of things that help with the design of ML infrastructure. So all of these are basically from our book, which is around machine learning design patterns. And the particular theme of the things that I'm going to talk about today is all about productionization of machine learning. This has long been understood as being one of the hard things. It's relatively easy to build an ML model, right? You can go into a Colab notebook and happily train a model in a few minutes, and you have your model. But how do you take that model and put it into production? How do you integrate it into the rest of your systems? That turns out to be hard. And that's what like this quote is about, that it took me 3 weeks to develop the model, but it's been 11 months and still hasn't been deployed. And that's a very common concern and complaint. This was a 2018 quote, but even today people say the same kinds of things. But over time, we've basically found that there are best practices that we can apply to simplify a lot of common problems. So this difficulty of productionizing ML models is an example of a common problem. And if you want to solve it, it's good to basically go look at other people's experience, right? You don't have to basically go through failure yourself. You can look at what other people have done. What have they done to basically get over it and apply their best practices? And in software engineering, we call these design patterns. And there are now design patterns in machine learning as well, because machine learning has been used in industry for close to 7 or 8 years now. And that's been enough time for this kind of best practice knowledge to get built up. The problem is that if you're new to the field, you don't know what these best practices are, and you end up rediscovering them all on your own. So our point about this was to write the book, Machine Learning Design Patterns. And this was about capturing what is common knowledge among people who've been doing machine learning for a while. Okay, so when you read the book, you will find that there are things that you already know, and that is by intent. No one's going to be like, I know none of these 30 patterns. There are going to be of these patterns that you will have encountered before. There's going to be stuff that are new to you, and there's going to be things that you may not have thought about, right? You may have said, I'm going to solve this problem in this particular way, but you may not have realized that there are some implications, and we draw out those implications in the book. So today I'm going to talk about 5 patterns that all help you. Yes.
Your screen's not sharing. I wasn't sure if you had something that you were.
Oh, yes.
Sorry.
Okay, I guess when you took over the screen, it went away.
There we go.
All right. So thank you. Okay. So I'm talking about the book, the ML Design Patterns, right? I'm saying that we're going to be sharing like 5 design patterns today. We're going to be talking about all of which have to do with improving the productionization of machine learning models. Okay. So the first pattern that I want to talk about is a pattern called transform. Okay. Imagine that you're writing a machine learning model, and the purpose of this model is to predict how long a rental trip is going to be, right? So if somebody rents a bicycle, somebody rents a car, and you say, okay, they rent it at this particular location on this date, how long are they going to keep that bicycle, right? So you're basically trying to build a model to predict the length of your rentals. So now the question is, how many inputs does the model take? And really, when you think about it, the model will be trained on 3 inputs: the station name, the day of the week, and the hour of the day. But we don't want to call them inputs. We want to call them features. There are 3 features to the ML model and 1 output, which is the duration. However, the day of the week and the hour of the day are both extracted from the time in which the rental started, the start date. So there are 2 inputs, 3 features to this ML model. So this process of going from your inputs to your features is called the transform. Okay. Why do we need that transform pattern? Okay. So imagine that you have these 2 inputs, and we do a bunch of pre-processing of those inputs, and then we create new features. So in this case, we've basically done pre-processing of the start date to create the day of the week and the hour of the day. So we've created these features, and then we train the model with those features. We deploy the model. That's great. Now our client comes along and they say, here, I would like you to tell me how long this rental is going to take. How many inputs does the client need to supply to your model? Do they supply 2 inputs or 3 inputs? 3, right? Because the model was trained at 3 inputs. So they've got to give you station name, day of the week, and hour of the day. Now you have a huge problem when it comes to productionization. And the problem is this. How does a client know whether the week starts on Monday or Sunday? If they rented the bicycle on Tuesday, should they give you TUE or should they give you the number 2? The hour of the day, should they give you 7 p.m. or should they give you 1900? Point is that you don't know any of these things. And that becomes a tremendous problem, because when you now go ahead and try to call the model, you need to call it with the features. What we really want is to call it with the original input variables, your 2 inputs. You don't want to have to produce 3, because this whole pre-processing and feature creation, that's internal logic in your model process. However, your model was trained on 3 inputs, and that becomes a problem. So if you were to take the scenario what I'm talking about, we basically had the duration and the start station name and the start date. We went ahead and extracted the day of the week and the hour of the day from that. Now, when we do our prediction, we have to know what to pass in for the day of the week, what to pass in for the hour of the day. That's something that the person who designs the model knows. The person who's invoking the model, they don't know it. And this is the leading cause of training serving skew, because you will have different libraries on both ends. You will have a Python library. When you did the training of the model, you'll be calling the model from PHP or Java, and maybe the way they compute the time is different. So you basically have all kinds of issues. So how do you resolve this problem? The way you resolve this problem is with a transform design pattern. So what you do is that you keep your inputs and your features separate from each other. So here, that's what we're seeing here. These are the inputs, the duration, the start name, and the start date. So you have 2 inputs, start name and start date, and then you transform it. So you basically have your transform clause where you say, I'm going to take the day of the week, I'm going to extract it as the day of the week, and I'm going to extract the hour from the hour of the day. Now, this means that the model has contained in it the transform logic. So now when you do the prediction, you can simply pass in the station name and the current timestamp. Notice how beautiful this is. The client doesn't need to know what pieces of the entire date you're actually extracting out. All of that is incorporated into the model itself. So that's the key idea. If you want to make productionization easy, you basically let the client pass in the input variables and you store all the transformation logic inside the model itself. Okay. So how do you do it? So what I showed you was BigQuery SQL. So that was a SQL data warehouse in which you can do machine learning. What if you're doing TensorFlow and Keras? Well, in those cases, you want to make sure that they are part of the model itself. Well, how is something part of the model in Keras? It is part of the model in Keras if it is a layer. So what you have to do is don't do your pre-processing in pandas or something like that, but do your pre-processing as a Lambda layer in Keras. So make sure that you do your pre-processing in a Lambda layer in Keras, and then it is part of your model, it's exported as part of your model, becomes super easy to move it into production. So bottom line, the transform pattern, moving an ML model into production becomes a lot easier if you remember that your inputs, your features, and your transforms, these 3 concepts. They're 3 separate concepts, right? And you want your prediction to pass in the same as the inputs, where even if the model is trained on features. And the way you do this is by storing all your transformations as Keras layers, not as whatever you do it today. Okay. So the transform pattern, the basic idea is the model graph includes all of the transformations. Okay. So, right, if you wanted a meme, right, it's basically, hey, put me in the graph, coach, right? That's the basic idea. Put all your transformations into the model. Do not to keep your transform code separate from your model. And as long as your transform code is in the model, it will get exported along with the model. So during prediction time, all of the transformations will automatically get applied. Okay. Second pattern idea is this idea of a multimodal input. So take, for example, you want to basically predict whether this particular car making a left turn is in violation or not. And you basically get an image and you pass into your ML model and you say, is this a traffic violation or is it not a traffic violation? The problem is that this image by itself is not enough. You also need to know what time of the day it was taken on, right? So is this an image classification problem? Yeah, it is an image classification problem because I have an image and I need to classify whether it is a traffic violation or not a traffic violation. But do you know of a ResNet image classification system that will allow you to pass in that numerical feature? Nope, right? An image classification model wants an image and that's it. So how do you deal with this case where your input is multimodal? You have an image and you have some structured data. Okay. The basic approach that you should do is that you need to basically take all of your inputs and create representations of them and concatenate those model representations. So the pattern here is whenever you have something like this, you take your image, you pass it through an embedding layer or convolutional layers, your ResNet with the final, like the top removed, and that is one side of the equation. On the other side of the equation, you have all of your tabular data. You take all of the tabular data, you again pass it through a set of deep neural network layers, and then you concatenate the two, and it is that concatenated layer that you then basically run your softmax on, or you run your sigmoid on to basically go ahead and do your classification problem. So the bottom line is that even you have data of different types, you basically build parallel models and you concatenate them in the model graph. I mean, it's still one model that you train, but this model that you're training is a multiple model graphs that are all concatenated. Okay? So if you take, for example, text, right? So one of the common questions that we get is, hey, this text thing, should I use bag of words? Should I use word to vec? Should I use BERT? What should I use? Should I use swivel? I have so many different embeddings. Which one should I use? And my answer is, why do you have to choose? Use all of them, right? So you have multiple ways of representing the text feature. So you can take your text, you can embed it, you can do bag of words, you can do swivel, you can do BERT, you can also do feature processing. You can find the length of the review, you can find the sentiment of the review, you can find which language it was in. You take all of these things and you concatenate them and you pass them into your model. Okay, so the basic idea is, right? So whenever you find these questions, should I use BERT or universal sentence encoder? Should I use bag of word or should I use glove? Should I do from scratch or should I use transfer learning? Right? The basic meme is, why not both? Right? You can always do both. Simply do a multimodal input, concatenate them. Right? So you can have multiple model graphs that all capture different aspects of the information. Third pattern idea is this idea of a workflow pipeline. Okay? Your typical development workflow that you do, right? If I'm developing a model, you collect the data, you validate the data, you pre-process it, you build a model, you train it, you evaluate it, and finally you deploy the model. This sounds very much like a waterfall. You go from one step to the next step to the next step. But that's not the way life is. Usually what happens is that you're doing experiments. You're doing a lot of ad hoc things. So you've collected the data, you validated it. When you train the model, you discover that the way you pre-processed the data was not correct. And you come back and you want to start at the pre-processing stage and do some amount of pre-processing. And then you want to change your model and retrain your model. So you do a number of these experiments that are pretty ad hoc. And then at the end of the day, you say, yeah, at 2 o'clock, I did this thing that was the best. What were the things I did again? I kind of forgot, right? So you've lost the track record of all of the changes that you've been doing to your notebook. So how do you deal with this? Okay. Another place where you have this problem is when you have hyperparameter tuning, right? You basically do your data preparation, model training, and evaluation, and then you train your model, and you do it with a different parameter set and a third parameter set and a fourth parameter set, and you compare the model, and there's a lot of repetition between each of these parameter sets. And the question is, can we not share? If the data preparation doesn't change between A and B, can we not share the output of the data preparation step between A and B and use it to train the two models? Or if the models are the same, but they're evaluated in different ways, can we not basically change them? Right? So how do we avoid this wasteful repetition when we do things like hyperparameter tuning? Okay. The way that you do it, the third reason to basically use a workflow pipeline is because with machine learning, unlike with traditional DevOps, you often need to validate the whole system. You need to validate the data, the schema, the models. You want to monitor things, you want to retrain them, and you want to do them in a repeatable way. Okay? So the answer to all three of these problems, what are the three problems? The first problem is that you want to basically keep a record of your experiments. Second problem is that you have a bunch of steps that you're repeating, and you would like to take advantage of the output of previous steps so that you don't have to repeat that step again if nothing has changed. So you want to take advantage of that automatically. And the third thing is that you want to be able to do things like continuous integration, continuous deployment. You want to treat the entire set of steps in your machine learning process as a single work item that you can just execute all at once. The solution to all of these is to basically represent your ML workflow as a pipeline, where a pipeline is a directed acyclic graph, and each of the steps in the pipeline is itself something that can be executed by itself. But what it does is that it produces what are called artifacts. It produces artifacts that are stored in persistent storage in very carefully thought out ways, so that if you now bring up another pipeline and there's nothing that has changed about a particular step, the pipeline will automatically go pull out the output, the artifact of a previous run, and reuse it, right? So there is reuse built into this whole idea of a pipeline that the pipeline automatically gives to you. And you basically can do branching. It's just that you don't have cycles, but as long as you don't have cycles, you can basically, in this case, as you can see, we are trying out 3 different models, but you're doing them all in parallel. That's an example of the hyperparameter tuning. And if I restart this pipeline, and if I already have pre-processed data that I'm not changing, my new pipeline will reuse that pre-processed data. It won't run the pre-processed node all over again. So that's the basic idea here, right? The idea is that each of these steps that you're doing can all be done either individually, they can share artifacts across runs. You also have a complete record of every run that you have done. You can always go back to a previous run. You can look at its logs. You can look at its output, right? So that's all repeatable. And in order to do that, every step of the pipeline becomes a container, and all of the dependencies are captured, and all of the logs, all of the outputs are stored in very specific ways, such that all of the parameters and data that's passed between the steps is stored in that artifact repository, so that the next time you start a run, if nothing has changed, it just pulls that up. It doesn't rerun that step. So you get that efficiency as well. Now, there are multiple pipeline systems. One pipeline system that we use a lot at Google is called TensorFlow Extended. And this basically allows you to do experimentation, training, continuous training, model serving, and monitoring. So you basically have components that help you do all of these things so that your code can be in Python, they get wrapped up, and they can get run on a Kubeflow container, for example, in such a way that you are kind of insulated from all of the infrastructure management. But the key idea is that between every two steps, there are artifacts, and these artifacts get stored and can be pulled up whenever you want for repeatability. Okay. So the idea behind a workflow pipeline is that you have a pipeline DAG that's executable as a whole. It's executable one part at a time. It's triggered by different events. And then you can basically, all the artifacts are stored in a repository. And you basically have a number of pre-built components to basically get started with things like training and evaluation that everybody does. So you don't have to go build your own, like a training component. You can use a training component that the pipeline framework already gives you. So we've looked at like 3 patterns, and they're all kind of related to each other. Okay, a data representation, right? Multimodal input is an example of a data representation pattern. We said that if you have different possible representations, you can concatenate all of them and use them all together. And when you're doing that, how do you make sure you're concatenating it all the same way? How does your client know that they need to give you all of this data ordered in this particular way? Well, they don't. So it's much easier if you have a multimodal input, if you use it within a transform. So you put it into the model graph. And again, the idea behind a transform pattern is that you explicitly capture and you store all of the transformations that are needed to convert the model inputs into features, and you put that into the model graph. And again, how do you make sure that you're having it in the model graph, but you're not wastefully running the model over and over again? Well, you can do that if parts of the model graph are their own functions, and they're all part of your ML pipeline so that you don't have repeatability problems. So as you can see, right, each pattern can be used by itself. It gives you a lot of benefits, but understanding the relationship between the patterns means that it makes it much easier to implement a pattern. It makes it makes a pattern much more resilient, etc. Okay, and there are a couple of patterns that are related to these things that I didn't talk about. For example, the Cascade is an alternate to having the multimodal input. A feature store is an alternate to having the transform. And there are specific cases where you might want to use a Cascade or a feature store over the more simpler solutions that I talked about, where multimodal input and transform are the simpler things. Cascade and feature store are more complex answers to somewhat related problems. Okay? And so part of the book has a bunch of these connections between the patterns. How are these patterns related? If you're using a feature cross, you should always try to use it with an embedding. Otherwise, you will run into dimensionality problems, right? So advice like that is part of the book. So I talked about feature store. I said a feature store is like the more complex thing. What exactly is a feature store? Well, a feature store is going beyond a single ML pipeline. What I just talked to you about, an ML pipeline, a single pipeline, that only happens in toy problems. Whenever you look at a real world problem, there's multiple machine learning models built into it. I think yesterday the Google Photos team announced this new model that would basically, when you look at a picture, it will basically understand the depth in that, and it'll basically zoom in and out. It'll just give you a little bit of movement on that. And there's a beautiful blog that talks about all the ML models that go into that very simple capability. Stuff like object detection, segmentation, depth analysis, being able to do corrections, and finally some old-fashioned constrained optimization. So you basically have all of these models that need to run one after the other that all connect together, and that's your real-world ML model for you. So when you have that, it is very, very, very common that many of these models will use very similar features. So what a feature store does is that it basically says that if you're going to be using a particular set of transformations on a particular type of data, and you're going to be reusing those transformations over and over again, it's much better to store the transformed data, the features themselves in a database, and provide them to the rest of the system. The problem is that when you're providing the features, you have two different types of users. You have the training users who will want to get all of the features corresponding to a batch of examples. So they want batch access. And you will have serving users, the ones that are using it in real time. They're going to give you one instance, and they'll want the feature for that one instance. So they'll want low latency inference. And the ability to basically handle both of these means that the design of the feature store has to be pretty complex. It has to serve both low latency users and batch users. And so you're better off using a feature store that's been well designed. And it's one of those things where pretty much every large ML team out there has built their own feature store. But we're now getting to the point where you'll start to see services that do feature stores, and it's much better to use a managed service that gives you a feature store rather than trying to build your own. But an example of building a feature store is something that a company called Gojek, based in Indonesia, did. So Google and Gojek together, we built a feature store called Feast. And what Feast is that it uses BigQuery for its training and Redis for its online low latency inference. So it's a two-headed beast that both basically are populated using the same set of pipelines, right? Your Apache Beam pipelines that end up populating both of them. Okay, and in order to do that, you basically have to remember that if you're going to be representing something like a driver in Feast, you have to basically think about the representation of the object and adding it into this feature store so that it can be used both for training and for predictions. Okay, and same thing, like when you're retrieving from Feast, you basically can retrieve historical features. You need to be able to get time aggregates, etc., which means you will have two different endpoints, one endpoint for training and one endpoint for prediction. Okay, so the reason to use a feature store is that whenever you need a feature, it's already pre-computed. So you basically get amazing reuse, you get standardization, you get speed. Like the purpose of a feature store is that amount of reuse and standardization. And the last thing that I want to talk about is a cascade, is that slightly more sophisticated form of a multimodal input. So when you have an ML problem and you want to basically break it up, so for example, if you're trying to predict if an item is going to get returned, it might turn out that different types of items get returned at different rates. So you might have a first model to predict, is this item sold to a reseller, or is this item being sold to a commercial buyer, or is this item sold to a retail buyer? And if their behavior is different, you basically have a classification model, and then you have your regression model that will predict how long it will be or whatever before the item gets returned. So the question is, when you're training this model, what is the input for this model? The input for this model is whether or not this item was sold to a reseller or not. We may have in our training data set a flag that says the seller type is a reseller. So is this what we need to do? We need to pull out the original training data set and filter it by seller type equals reseller and train this model. Or should we take the original transaction details pass it through an ML model that we have trained, look at the output prediction, and if that prediction is greater than 0.5, then we feed it into this model. Which should we do? Filter the input data, the training data, or filter based on the predictions? This one is easy because it's already in your training data. This one is hard because this model keeps changing all the time. We keep changing the first model. Okay. Unfortunately, though, if we train the data based on this, then every time this model changes and every error that it has, this guy will not have seen the errors before. And we really need model 2 to work well with the errors that model 1 makes. And because of that, right, you have to train the models all at once. You cannot train the first model, let it go, and then train the second model. Instead, you have to train this cascade of models together. If you don't train them together, then small changes in model 1 is going to cause dramatic changes in model 2. So the way you do this is that you basically make a pipeline that consists of multiple ML models, not a single ML model, and you basically train this entire pipeline as one go, right? So it's not about training a single model anymore. It's about training a cascade of models. And it turns out that this idea of training a cascade helps to simplify a lot of ML problems. So rather than training one big ML model, you train a cascade of smaller ML models, each of which can be trained with less data than you would need to train one big ML model. So there are lots of frameworks that exist when it comes to how do you simplify a cascading model. So here, for example, is a cascade solution called media pipe. That is, if you're doing face detection or face mesh or box tracking, then you can basically use these building blocks and you can train them all as a cascade, okay? And to reuse the existing components, and if you want to, you can tune those components and you can basically line up multiple models together and train them together. So bottom line is when you have a workflow pipeline, you can use it to automate the cascade. We talked about workflow pipeline as a way to basically do things like hyperparameter tuning. But what we're talking about here is that you can even use it during development. So when we talk about pipelines, pipelines are not just about CI/CD. It's not just about deployment. It is also about development. So when you're doing development and you want to basically train the sequence of models, pipelines become super, super helpful. So in summary, we talked about 5 patterns today, right? Multimodal input, transform, and workflow pipeline. And then we added 2 more, Cascade, which allows you to treat your entire ML system as a unified workflow, and a feature store, which is basically a centralized location for all of your document features. It allows you to build in more and more reuse among all of your features. So these are like 5 of the patterns that we talk about. And as you can see, a lot of these patterns, as you start combining them, they start getting into you absolutely need to have a workflow pipeline system built, because otherwise it becomes really hard to use transforms or multimodal inputs or cascades or feature stores. Like the list goes on and on. So you can do toy ML without a workflow pipeline, but you really need a workflow pipeline, right, to get the real benefits of doing large-scale ML. So with that, like I come to the end of my talk, read the book, okay? So bit.ly, okay, ML-design-patterns. Follow my co-authors and me on Twitter. So lac_GCP, that's me. Sarah Robinson is srobtweets. Read our blogs. Michael is this amazing person. He's not on social media. So he's like, I have a life. I have a real life. I'm not going to live on social media. So you don't get to hear what Michael thinks. You get to hear in detail what Sarah and I think. So, and also all of the design patterns in the book have implementations, example implementations, so you can see what they look like in practice. Those are in that GitHub repository. Okay, and with that, I will take questions.
That was awesome. So if anyone has any questions, please type it in the channel and I'll capture it. But I was gathering some questions that I had while you were talking. You had talked at the very end about the workflow, and you need to kind of utilize that. So it kind of leads me to wonder, are you finding that most people, when they're starting, that they are designing initially with a lot of these patterns in mind, or is this more like people are prototyping, playing around, and then they have to move and introduce these
Right.
patterns
That's
after?
a great question, and really comes down to the sophistication of the team. The more sophisticated teams design first and then build. And whenever you design first and then you build, a lot of these patterns come in. But if you're in a less sophisticated team and you're just starting with a blank notebook and you're starting with code, then lots of times like the patterns start to come in during productionization, and that's really the no. It's a bit late at that point. It's ideal if you could do it at the time because many of these things help you with design as well. But again, there's other patterns like feature crosses and multimodal input, etc., which are very much training time design patterns. So again, there are 30 design patterns in the book. Not all of them are about deployment. So I'll just go to the GitHub repository, not that book. ML design patterns. Okay, so these are the design patterns, right? There's some around representing data. There's some around representing the problems themselves. Things about how to basically make your model training better, how to make your serving more resilient, how to make your entire process much more reproducible, and how to do AI more responsibly. Right? So there's like, we're addressing a wide variety of problems in ML. Even though this talk was very much around, that gap between development and deployment. I don't want you to walk away thinking that the entire book is about deployment patterns. It covers a wide gamut of things.
Yeah, I was actually wondering about the responsible AI pattern, and if you could talk any to that. Is that something like where you just try to introduce those concepts into basically anything you're doing, or?
Right. So like the heuristic benchmark is something that's going to be absolutely applicable in every ML project that you do, because it is about how do you explain how well your model is doing to stakeholders, business stakeholders. And the way you do that is with heuristic benchmarks, and we basically have a table of stuff that you can do. Here's a bunch of like, in this situation, here's a good benchmark. So the book basically has a table of about, I want to say like 15 rows or 15 scenarios, and with each scenario, what's a good benchmark that people have found for that scenario. Explainable predictions is this idea that it is not enough to say my model behaves this way. You have to explain every individual prediction. You have to say that here's a loan I'm making. I'm not approving this person, but I would approve this person had this person had $3,000 more per year in income. I would approve this person had they had 2 fewer late payments on their credit card. Right, that's an explainable prediction right there. Right, that to be able to basically, how do you combine your prediction, approve the loan, not approve the loan, along with an explanation that makes sense to a real viewer, right? To a real person. It's not an explanation of this feature is the most important. I mean, who cares which feature is the most important in your model, right? What they want to care is, yeah, you can say income is most important, but it's much more tangible, right? The reason that you didn't get this loan was because it was $3,000 below the threshold for like somebody who wants to buy a house like this. That's an explainable prediction right there, right? So that's and fairness lens is about a lot of the things that can happen in terms of bias, right? And how to basically set up your data collection, how to set up your ML models, your training, your metrics, in order to ensure that things are equitable. And then once you deploy the model, what kind of continuous evaluation do you need to do to ensure that it remains equitable?
No, that was really cool. So we're getting a lot of questions about some of the specific patterns. So
Sure.
like what
Do you
the
want me to just look at the chat and run through the
I
questions
was going
one
to
by
try to
one?
bucket them a little for you. So like
Okay.
with the workflow one, there was a lot of questions as to, you know, how Docker containers factor into that, and if there's any patterns that make it easier to share workflow components. So really, is there any best
Yeah,
practices,
absolutely.
tools, and
So if you look at
technologies?
the workflow component, we said that each of these is a container. I mean, it's really a Docker container, right? So it depends on the implementation. So if you're using Kubeflow pipelines, for example, every one of these boxes is actually can be a Docker container. It doesn't have to be a Docker container. It can be a Python function, but the Python function will get wrapped by the framework and will be run as a Docker container. So ultimately, it becomes a container. Okay. So yes, there's containers that are the ones that the pipeline actually executes, but you as a data scientist may not have to deal with the container directly. The container might get created for you based on the fact that you write a TensorFlow program, or the fact that you write an Apache Beam program, or the fact that you basically have you invoke a TensorFlow serving saved model, right? Those are the kinds of things that would basically the containers would get created for you for those particular steps. That's what something like, say, TFX does, right? So TFX basically allows you to say, here's my Python function, wrap it up into a Docker container and run it. But if you want to create your own Docker containers, you can as well.
Okay, that makes sense. Actually, staying on the pipeline, the workflow, there was a question that just came in and it kind of made me think, like, are there tools and there's ways that people are handling like logging and monitoring across the pipeline?
Oh yeah, absolutely. Like, when you look at a production pipeline, okay, so ML pipelines on Google Cloud, for example, has the monitoring all built in. Monitoring, logging, saving of the logs, basically getting your dashboard of the logs. Those are all built in. You don't have to do it. I mean, you should not have to build those things. That's just infrastructure. Let your framework provider give that to you. You should focus on building your ML models, building your ML pipelines.
So there was two questions about the Cascade pattern. One
Mm-hmm.
was, is there any issue with the drift, given that the downstream models are sensitive to the outputs of the upstream? And does it
Yes,
structurally
there
reduce
would
error?
be if you did not use Cascade. When
So,
you're doing a Cascade, you're training it as a whole. You're training the entire system as a whole. And the reason you're doing that is to prevent the drift of the second model with respect to things that change in the first model.
and then there was a question as about um, if you is there like a good example that you could describe where the Cascade model really helps simplify a complex ML problem?
Yeah, I mean, there's lots of them, right? So again, because this is just top of mind for me, I would basically take the Google AI blog, because this is, I think, yesterday, and talking about like photos and I think movement, maybe. Yeah, behind the motion. Oh no, that's an old one. Okay, just do Google AI. Yeah, cinematic photo. So that was like, yeah. So something like this, right? To be able to do that is a number of ML models that are all lined up one after the other. This blog talks about some of them, right? You need to basically take your image. You need to basically figure out the object detection here. You need to do depth analysis, and you need to combine these two to do a segmentation corrected depth. That's a cascade.
No, that's pretty good. Actually, it leads into I think a pretty simple question for you. You listed some resources, and then you brought this up. Is there other resources that you really enjoy reading that the audience might like?
Uh, Again, I mean, it's like it's very difficult because are all online. I don't know the level at which different people are, right? So you have beginner resources, you have more advanced resources. What I would say, if you're new to machine learning, I couldn't recommend highly enough the like Lawrence Moroney's course on like TensorFlow and machine learning. If you're technical, for non-technical audiences, Andrew Ng's course is really good. Again, I'll be biased here. On Coursera, if you go look on Google Cloud, we have machine learning with TensorFlow and advanced machine learning with TensorFlow. And I was involved in the creation of those courses, so I obviously think they're very good. Okay, so there's several resources. Let me just plop that out here. Coursera, Google Cloud, machine learning with TensorFlow. So let's see. Yeah. So this is the one I talked about, Lawrence Moroney's TensorFlow machine learning, but also machine learning with TensorFlow on Google Cloud. Okay. So now, if you're interested in the combination of TensorFlow and production, so this one and the one that follows it, which is called advanced machine learning with TensorFlow, that gets into the more advanced concepts. So these two courses are, I would really recommend them.
So in those courses, do you kind of talk about the patterns, some and the tools and technologies you mentioned?
These courses were done before the patterns book. So you will see some hints of the patterns here and there, but not the patterns themselves.
Okay. There was a question if you had any advice or tooling for how to aggregate and manage the serving of multiple models.
How do you manage and serve multiple models? Again, all right, the best thing is to use an infrastructure provider that helps you do it. Again, I'll be biased. I'm from Google Cloud. In Google Cloud, we have something called Cloud AI Platform Predictions that allows you to specify a container for serving. And within that container, you can basically load up all of the separate models that you want to do, and you can basically serve them all as one thing. And so that's how I would recommend doing it, right? The huge benefits that come from direct container support and that speed of being able to execute the container, auto scale it, run it on a GPU, right? Those are some of the benefits that you get by doing that. And you can, inside that container, you can basically use the traditional typical Python programs to run each of the separate models and basically coalesce them.
That was really cool. So I actually had a question myself that's a little different, not related to the patterns and everything, but you're talking about ML ops and things. And I think I asked this to a previous speaker. Are we really seeing more and more specialization and separation of roles and responsibilities where folks are developing the models and managing the workflows and managing all the underlying tools that you mentioned?
It really depends on the size of the team. Okay, so basically, I see broadly the following roles. A data analyst who is somebody who basically understands the domain, understands the business, is able to look at data and help people make decisions, but is not doing much automation, right? They're solving highly unique problems, okay? Then you have a data engineer who's basically building a lot of the data pipelines to supply the data into the data warehouses and data lakes that power the analysis jobs of a data analyst. And then you have a data scientist who is looking at the kinds of things that the data analyst is doing that can be a bit more repeated and looking at how to automate them and do them at scale. So where the data analyst might do stuff once a day, once a week, the data scientist is like, how do I do this on every transaction, right? So that's about the scaling aspect of it, and to do this much, to do things like personalization or to do targeting or to do the fault identification much faster. That's what a data scientist does. An ML engineer basically is taking these models that are being built by the data scientist as an experiment, and they're often taking them and putting them into production. They're monitoring it for drift. They're basically doing the continuous training, continuous evaluation of it. So 4 roles. Not all companies have all 4 of these roles. In many cases, a couple of these roles get combined. So in many companies, a data analyst and a data scientist, the roles get combined. There are some things that you will do that are scalable, and there are some things that you will do that are one-offs, right? That's the kind of thing that you've combined the data analyst and the data scientist role. In some companies, a data scientist and the ML engineer get combined. You will build models and you will put them into production, right? In some cases, the data engineer and the ML engineer get combined. You will bring in the data and you will maintain the APIs for serving the models because they're both back-end infrastructure. Okay, so it varies. It varies of how it is that you do, but there are 4 roles. But some of these roles get combined depending on how large the company is, what the tradition is. Now, a lot of companies divide on front end versus back end, and such companies often combine the data engineer and the ML engineer together. Lots of companies divide on science versus engineering, and those companies tend to combine the data science and the ML engineer together. Okay, so basically it varies.
No, that was awesome. Thank you. So I think last question. I was kind of looking at your book a little, and I saw that each pattern you had a section that kind of talks about like the trade-offs. So I was actually
Yeah.
wondering, like, can you talk a little about that? And are there cases where you've run into where you actually intentionally didn't use a pattern?
Oh yeah, all the time, all the time. Right? Again, those trade-offs are super important. Okay, because we're talking about, like, for example, like a very simple pattern, a feature store, not a feature store, no, a feature cross. A feature cross is basically a way in which you get to use much simpler models by increasing the parameter space. So that's great because you want simpler models. But what a feature cross does is that it increases your memory requirement tremendously. Okay, so that's your trade-off right there. What do you care about? Do you care about memory usage or do you care about speed? Do you care about simplicity or not? Right? And that's a real trade-off, and you will have to make that decision when you use an embedding. You're basically encountering loss. How much of loss is acceptable to you is an important consideration. So you might take a feature cross, follow it with an embedding, to basically say that, okay, I want this large parameter space, but not too large, right? And you basically start to do that adaptation. And those are, again, there's no correct answer to any of these things. That's why these are patterns and not things that are just done for you, right? In a framework. If it were straightforward and it's always good, it would be the thing like just now we will automatically do it for you, right? Keras will automatically take care of it. Okay, but it's this is not one of those things.
So last question, Lek. I think this is a good one to end on. And you kind of talked about it a little because you were throwing a lot of some of the tools out there. But I guess someone who's trying to learn more and get started, are there recommended tools and technologies for use to do a lot of this stuff? I mean, you kind of seem to be talking a lot about the Google ecosystem, and I understand why.
Of course, I work for Google. I'm very biased, right? Obviously, I'll say, like, all of these patterns, like, you can obviously, if you use the Google ecosystem, we've talked about these, we've thought about these things, and we've designed them to basically make them easy to do and easy to implement. The other thing is, like, when you're starting out, again, along with the book, we basically have, like, you say, okay, how does a feature cross work? Well, there's a feature cross. There's an IPython notebook right there. You can go read through this notebook and basically say, okay, this is exactly what a feature cross is, and this is why you do a feature cross. So here's a feature cross in Keras, and this is how you implement it in Keras. Keras is open source. So even though I'm saying they do it on Google Cloud, right? It's totally, we're here about talking about the concepts and how to implement them, right? And how to use them.
Yeah, that makes sense. I think it's really interesting how there's seems to be like application tools for all the patterns that make it a lot easier. So you can kind of use a lot of the patterns and do best practices, and someone's kind of
But
done
you
a
just
lot of
have
the
to
heavy lifting.
know. Yeah, you just have to know what they are, and should you use them? When should you use a hashed feature? When should you use a feature cross? Right? Use a hashed feature when you don't have a vocabulary. Use a feature cross when you do have a vocabulary. Who's going to tell you that? Right? So, right? That's the thing that the book does. Right? The book does that thing of, what are the trade-offs? When do you use it? Yeah, both these things exist. When do you use what? Is an important thing about design patterns.
Yeah, no, that's cool. Well, I think that's a good place to end it. I think that was a good overview and a nice introduction. And I think folks that are interested definitely can follow up with all the resources that you provided, especially like your book. Like you said, there's like I think 30 patterns, and I was looking at it pretty quickly, and you go into a lot of detail in each of those. And with all your talks, you definitely can get more information. The slides, I'll talk to Lack about them being available, but if not, the GitLab or the Git repo that he has up has a lot of information also that I saw. So I'll try to get that posted into the meetup group also. Um, but I guess that's a good place to end, Lack. I really
Thank
appreciate
you
you
very much,
taking the
Jason.
time.
It was, it
Yeah.
was, it was great talking to you all. So, thank you very much.
Yeah, it's really interesting to hear from someone who's so involved and an expert, and I can only imagine the cool stuff that you're doing over there. So well, thank you, Lack. With that, I'm going to end it. I hope everyone, joins us next month. And if anyone needs anything, reach out and have a good evening, Lack. Enjoy the rest of your beautiful day over there on the West Coast.
I was just telling Jason before everyone got on. It's one of the beautiful summer days, and it looks like a summer day in Seattle. It's sunny. It's just gorgeous. So we're really enjoying it today.
That's great. All right. Thank you. And good night, everyone. And see you next month. Thanks.